Here we go. So my last presentation, we were talking about specs. How do you make sure that your building's going to come together and so on. And I made a few comments there about materials, and you need good material specs and so on. And I showed you the peanut butter slide. So I'm not going to tell you why I showed you the peanut butter slide and why I got a slide that has peanut butter on it. And what I'm going to do is I'm going to show you a couple of material specifications and all what is requirements and so on and so forth. And then the main point I'm going to try and get across is if you read a material spec, almost all of them will have a clause in there that says, this is for quality assurance in comparison of materials. This does not indicate end use performance. So why are you using that in your spec? Well, there's reasons. So why properties matter, what's most critical, evaluated materials, and how do we do new stuff that's coming in there. So air barriers impact almost everything in the building. We think of it moisture management and we think of some energy, but a proper sealed building makes almost everything else work better. The mechanical system is going to work better. The mechanical system has a hard time to put air in this room if there's holes all over the place. It's really hard to balance it. I was down maybe a month ago in Los Angeles to the Balancing Association, and my point is you can balance it, but an hour later you're imbalanced because temperatures change, winds change, and all the rest of the stuff. Windows. I have a slide not in this presentation. It's in a cold climate where there's no connection between a patio door and the wall. And there's a big hole, and I used a really sophisticated means to know that there's a hole. I put my fingers through, and the whole frame was all frosted up. Now, the worst part of your window is the frame. The best part of your window is center glass. And so when you have air leakage, especially cold air leakage going across the frame, you're super cooling it, which you're really dropping the U value of your windows. And then we get into occupant behavior. People don't like to hear their neighbor, smell the cooking, concerned about viruses these days. They don't want to hear the sound. They don't want to hear them on the phone and so on and so forth. So it almost everything in a building is affected whether you have a nice airtight building. And as we go to net zero, high performance building, passive house, whatever terminology you want to put there, we have to have really good building envelopes for everything else to work. If we don't have a good building envelope, all the solar and wind and everything else and geothermal or whatever else you want to throw in the building isn't really going to work. Okay, so we get to the peanut butter. And the whole point of this slide was if I do a presentation like this and we talk about you need more than just air permeance or the air leakage rate of materials, you need other things. And I said, if the only thing we're concerned about is air going through a piece of material, peanut butter or Jello would work. I had nothing to back me up. But I was at a codes meeting. Anybody have been at a codes meeting? I'll go. The iCodes, the ICC generally have 2 weeks of code meetings, and they generally go from 7 o'clock in the morning to 11 o'clock at night. And your part there is probably maybe 30 minutes, but you don't know when it's going to be. So you have to sit there and listen to absolutely everything. But the good side of this one is I sat beside a guy from a testing agency. And I think he just wanted me to shut up. So he finally agreed to do a test on peanut butter. So it's a ASTM 82178 certified test. Okay, there's their specimen. We put it on CMU and we put it on 20 mils wet because any fluid applied, the thickness is really critical. And it was Kraft. So I don't know about Peter Pan or Skippy or anything else out there. It's smooth, so I don't know if chunky would work. But we ran it. Any guess of how we did? Yeah, did actually really good. Well, this is in liters, so the maximum air leakage can be 0.02. We threw another 0 in. And that's quite typical for all airborne materials. You're never, if you go to Imperial, it's 0.004. almost every material, these guys in the room here, if you take a look at the air leakage rate of their material, put at least another 0 in there, sometimes 2. So we do some really tight. So I've been at this with ABBA since its inception. So I was going to change my life. I was going to come up with the most friendly, environmentally friendly air barrier you've ever seen. You probably get lead credits because most of the stuff is growing within 100 miles of your project. And you know, if you get storms or floods, you can heat your house. I had all these things lined up, and so I was going to quit my job, and that was going to be my retirement. And then people started pointing out things to me, like there's a whole lot of people that's allergic to peanuts. Rodents love peanut butter. You want to trap a mouse, you put peanut butter on the thing. And when it dries, it cracks, and so on. So I'm still here. But you know, the bottom line, would you use it? Now here's 2 different materials, and just to reinforce the point. What's the air leakage rate of these materials? Both of them. Almost the same. Okay. So the whole point I'm trying to make, you got to go past just air permits, air leakage rates. And a guy named Neil Hutchinson, now this goes back, he was with the National Research Council, and in the 80s they were doing a lot of work on air barriers and why. And it really stems from the 40s, late 30s and the 40s, the University of Minnesota, because they were trying to figure out why we get water in walls. And the result of their work was the birth of using a water-resistant barrier or a building paper. In those days, it was 15-pound felt. It was real felt impregnated with asphalt. Today, our building paper is nowhere close to what it did. And you put it on the outside of the building, and guess what? The water didn't come in the building. So they thought everything's great, we can go home. In the 60s is when we really started to put in some insulation into walls. Before that, we really didn't care. You know, gasoline was sold for 25 cents a gallon in those days and so on. But we were still getting water in walls as we put insulation in the walls. So, okay, where's it coming from? Well, it's not from the outside. We can show it, we can prove it. Well, then it's got to be coming from the inside. Vapor barriers were born. So that was the mantra in those days. You have to have a vapor barrier in your building all over the place. And we still had water in the walls. So where the heck is this coming from? It's not coming through the material. We got water shedding on the outside. What's left? Well, that's when air leakage started to be concerned about. So there's a tremendous amount of papers written on the whole history of air barriers and how the calculation that we do for airflows and the whole bit. Most of it goes back to the 70s, because in the United States, we had what was called the OPEC oil crisis. By the way, it's deja vu right now with the same type of thing. And I always say, well, of course, you know, with the OPEC oil crisis and so on, back in the 70s, and I get somebody at the back of the room goes, hey, dude, I wasn't even born till 86. But it's important, that 70 is important because the Department of Energy spent a whole lot of money getting you and me and everybody else to improve our homes, improve our business. You know, we're going to reduce the amount of dependence on oil from other countries and so on and so forth, because OPEC had shut off the tap. And so there was lineups at the gas stations and concerns about heating oil in northern New York and so on and so forth. So we were going to solve the problem. Well, we didn't do a good job. And so into the 80s, with all this insulation going in and no air leakage control, and I know it even in the city I live in those days, in November, you would see the insulation truck come. It was really easy and cheap to do attics, so that's the first thing everybody did. All this insulation blown in the attics. Come April, you see a guy taking the insulation out in buckets because it's full of moisture. So then somebody says, well, what's the problem? Well, it's ventilation. We don't have enough ventilation. So we put more on. And there's a product called a turbine vent. Anybody know what I'm talking about? So it's a whirlybird. That was one of the brand names. And you put it on the roof and it swirled. And as it whirled, it sucked air out of the attic. Problem solved. It depends. And for you to have air come out of your attic, what do you need to go into your attic? Yeah. Cubic foot of air leaves, cubic foot of air comes in. Where do you think it was sucking that air from? Yeah, the house. So you would see in the middle of December, it's frozen shut. You can't twirl because it's frozen in place. And then the next year you saw a garbage bag, a green garbage bag over the whirlybird because you didn't want it to work. And then the next year you saw it gone. But we learned from that. So the Department of Energy today says they won't be involved in any project adding attic insulation without the air sealing of the attic. But all these things were happening. And so all those failures actually helped us. We had a tremendous amount of building science designed in those days. North America was deemed to be the leader in the world and all these type of things. We sort of lost some of that stuff, but that gets back to the work that the National Research Council, Neil Hutchinson, and basically he said, and this is really important, that you can't deal with an air barrier unless you look at all the layers. And what he said is he went back and took a look at what are we trying to do with walls? And you can apply this to foundations and roofs and everything. You got your loads, and of course this doesn't work. You got your heat flow, you got air flow, vapor flow, rain penetration, or let's say water flow, water resistance. Those are your loads on your building. Nature likes everything to be equal. So wet always goes to dry until they're equal. High pressure always goes to low pressure until it's the same. Hot goes to cold until they're the same temperature and so on. And so we don't want the temperature outside. It's kind of probably a nice day outside, but if you're here in February, you probably don't want the atmosphere that we have outside in this room. We want to be comfortable. We complain when we're too hot or too cold or too wet or too dry and so on. So we want a conditioned space, and that's what the building envelope gives us. So we have to put barriers up, and that's why I use the term barriers rather than retarders and so on and so forth to keep those out. And then he had other barriers, which is radiation, noise, and fire separation. And it's kind of interesting. One of the biggest increases in lawsuits is noise. You spend $1 million for your condo and you can listen to your neighbor. You're not too impressed. So the owners of buildings are being sued more and more for noise. And so in this area especially, we've had a lot of discussions about interior air barriers. How do we separate this room from that room if there's a reason to do it, and so on and so forth. And then you get the general strengths, rigidity, durability, aesthetics, economical, constructible. You can draw it, but can you actually construct it? And then a maintenance that's needed on there. So when I got a call saying, you know, what is the best air barrier I should put on my building? First of all, I'm smart. I go, it depends. And then we walked it through. Well, how are you doing your walls? How are you doing the roofs? How are you treating heat flow? How are you treating airflow? How are you treating water vapor transmission and so on? And as you go through and think about those things and apply it to a particular assembly, you start to understand how things are going to work. Kind of. And I'll go through that. So I showed you these before. We have the performance requirements. The bottom one says for a whole building, you should have a half a liter. We actually should be down to a quarter or a tenth of a liter. That's about 0.10 CFM per square foot on there for air leakage. We can do it now. It's not that hard. We've started to understand that. But we're going to walk through. So I mentioned a couple of times we call air barrier materials a big pieces. And that could be buckets and rolls or sheets or whatever it is, but it's the main material that we're using to provide the plane of air tightness. And then we have the accessories, which joins things together. Some examples of different ways that we can do that. And then we have the components. I said these are pre-manufactured. You don't touch them, but you just connect to them on the job site. All part of the air barrier system, and we have to have roofs, foundations, and walls. Andrew showed you some issues with air barriers and roofs, and there's a lot of evidence that the air barrier should be a separate material from the roofing material, but again, it depends on the project and how you're doing it. And we have the same issue, just going back here, like we talked about penetrations in the walls and windows and so on. Same thing with your roof. And so the two ASTM test methods for testing roof assemblies has those type of penetrations in the roof before they do the testing. And so how much air leakage you have when it's not just a single piece of material going across there. So that's an important test that's out there too. And then you have the whole building test. This is probably 10 years old. This is in South Korea. I was invited to come over along with a representative from Germany representing the European Blower Door Association, whatever it's called. And we did what we call a whole building rodeo. And I'm using that term because we provide air barrier rodeos where we would talk to you for a while, and then we'd have a place where we'd have mock-ups, and we would give you the air barrier material and get you to install it. Why do you think we want to do that? Why do we think we want you guys to go out that door and put air barrier on a mock-up? Remember, no wrong answers. Yeah. It's not that easy. And please take this in the right tone. The person that absolutely guarantees you that he did or she did the best job of installing is the worst job. Because we test it. We put some pressure difference, get a shop vac, put some chemical smoke in, and watch it come through all the holes. Why is the know-it-all the worst installer? Yeah. They're not looking for the little weaks and, oh, I know what I'm doing, slap it up, go home. So anyway, we're doing the same thing. And as I mentioned, we just launched the whole building testing, training, and certification. The training course is going on this week and so on. And we're going to do some of that in this area too. And what we did there is we had a building, it's a 4-story building. We invited the design community to come in to take a look at that. And then we actually walked them through the test. So we set up, we conducted a test, and we went from room to room, looked at where the air leakage. We wanted to accomplish two things. We wanted the people to understand that the whole building test is really not that hard. It's not some mystical thing that you do something to it and so on. It's pretty straightforward. And if you use things like smoke and so on, you can see the air leakage, and then you start to understand why. Where's that hole coming from? Why is it coming through there? Now, we do this all the time. We start to guess at where's the tightest and where's the most leakage part of the building. Third floor is a cafeteria. It's got equipment. It's got a duct that doesn't have louver on, because you can't put louvers on exhaust vents where you got grease and everything like that going through it. So, well, that's going to leak like a sieve. Went up to the top floor. It's a classroom, meeting room, whatever you want. Not too much there, no demising walls, no nothing. That's going to be pretty airtight. Remember, I said it was 10 years ago. When we tested it, it was actually flipped. Even that we had a big hole, I'm going to say about 30 inches in diameter of a duct going out, but they had done a lot of things to reduce the airflow, unintended airflow. That was actually a pretty tight floor. The top floor leaked like a sieve. Now we understand why, because nobody cares about the roof. We don't tie it into the walls and so on and so forth. But it was the whole thing that we did then and we want to do now here. Even though you've had whole building testing for a number of years, people are still afraid of it. They don't understand it and so on. And if you're going to do a whole building test, which is harder, run the test or prepare the building? And I'm not joking, you guys could all run the test because it's going to the computer and press enter. The manufacturers of blower doors have done a tremendous job of automating these things and doing the report. It even spits out the report for you. But it's preparing the building. And that's why the new standard E3158 is so important, because it gets into the details of why and how do you do the building. And there's 3 options. One is called an energy test. This is used in Europe all the time. You literally walk into a building, you set up the blower door, you hit the button, you walk away. And the reason why Europe is using that, they're saying, well, that's the building, that's the way it operates. If it's got a mechanical leak, if it's got a hole in the wall, we need to know because we're concerned of how much energy the building is going to use. Okay, makes sense. The other test is you seal big holes, but things where you have louvers and so on, you close them. So that is not just an energy test, because now we're starting to play with some of the holes. If we got a big hole for an exhaust duct and things like that, we seal that off because that's an intentional opening. We know it's there and so on. And we're trying to find where the air leakage where we don't know. Now, we said to close the grills and so on, but we don't seal them. And that gives you a combination of air leakage through the grills and air leakage through the walls. Again, good number. And you should do at least 2 of them. You should do that test where you just do the big pieces. And then you go, and your third test is for the fabric of the building, for the air barrier itself. And that you seal off all intentional openings so that everything is airtight, and the only way air can get through your walls or your ceiling or whatever it is through the holes that you can't see. And you can do those 2 tests very simple, very easy. So it's always good to do those both. They suggested a number of years ago that we combine them because we want to know how much the building leaks. The downside to that is the air barrier contractor has nothing to do with mechanical system. He can't go make sure the louvers are installed properly, installed the right way, not backwards, how good the ceiling is. They doesn't get paid for that. So the idea of a building air barrier or envelope only test is just to deal with the fabric of the building. But it's a good way to get the information out and get people to understand how easy it is. We talked about the key requirements. We talked about the impermeable material, and there's that same slide. And we talked about all the connections. That's where you're going to have the problems. And the other thing that when you're doing a whole building test or you're doing an air barrier, is where do you want to separate 2 environments? Okay, so you see this on one side, you got what I would call a roof with a ventilated attic. The other side, we have a cathedral ceiling, which is not kind of ventilated. But you need to trace on your building, and then down into the bottom, you have one where there's a foundation, a basement, that's conditioned space, and then you have what could be a carport underneath there. So you got to understand where your air leakage control layer is. And this is very basic, but you're going to get into some of the pictures that Andrew showed you. That could be very tortuous. And the air barrier doesn't have to be a nice straight line through the whole building. It can move all over the place. You got to watch, though, again, where you're placing the air barrier versus thermal insulation and so on and so forth. So it makes sure that you need to understand where you want to stop the air leakage. Talked about penetrations coming through walls and so on and how they can leak. So this is part of our training course for installers. You can see they're putting transition membranes on inside and outside corners because those 2 walls can move. And then you see a pipe coming through with, I don't know what the person's done. That's the first impression, but that's the proper way of making that seal because you want that pipe to be able to move back and forth without breaking the seal. One of the good things, and Andrew sort of showed, we're going a lot more to gunnable flashings rather than sheet flashings because sheet flashings trying to form in 3 dimensions are pretty hard. So that's the advantage of going to something gunnable. This is a real project. Let's assume it's your project. The contractor phoned me up and says, how do I connect to the window? What would be your answer? It depends. See? Building science expert. And it's true. So a bit tongue-in-cheek, I said, well, it's pretty easy. You take a piece of black asphalt and you slap it on the face of the window and you put it on to the air barrier that's an asphalt-based material there. They're going to bond good to the window. They're going to bond good to the asphalt. Problem solved. What do you think the owner said? That wasn't an option. And obviously I said it tongue-in-cheek. But that is a hard thing to fix. You got open parts of your frame. I mean, there's one manufacturer that does an air barrier window. And that's important because they've designed that window. They have flanges, and you attach your air barrier to the flange, but they've designed that from this flange to this flange that it's completely airtight. We need more and more manufacturers doing that. So even though we're the Air Barrier Association of America, we really want to work with the fenestration industries to understand what we need, because if they know what we need, they can help us get to where we want to go. And stack effect, we talked about that before on there. And here's the 2178 is actually for materials, 2357 is for the assemblies, 1680 is for metal roofs, and D8052 is for built-up roofs. So that is a big improvement. That's just happened, I'm going to say, in the last 2 to 3 years, where we have an assembly test. Again, it gives the contractor a fighting chance that's doing the roof of how do we do the air barrier on the roof. We saw that's your wall. This is the third. This is how you do the connection to the roof and to the foundation. You saw that pictures before. Now this is the loading schedule. So remember, we talked about an 8 foot by 8 foot wall. We do the air barrier on it. It's got connections. And then we subject to pressure. So it's 100 pascals for 10 seconds, and then 200 and 200. We actually go up to 600 pascals positive, 100, 100, 100, 100. And then we do the negative. We do 100 and drop it down. The next part is the cycle. So we have repeated positive and pressure at times, and then negative pressure, 2,500 cycles. And that's now at 800 pascals. And it takes about 8 hours to run this test because you're doing 5,000 cycles. Now, 800 pascals, what is that? How would you even explain it to people? Do we change it into a column of water? That's still here's the way I explain it. If you run this test with steel stud wall, exterior sheathing, the test I saw, it was gypsum, glass face gypsum board, put your air barrier material on, doesn't matter what it is. Center of that stud, it's going to move back and forth about 3/4 of an inch. And part of the test in 2357 is you have to measure that deflection. Now, when you start to see steel studs in the center moving back 3/4 of an inch, plus or minus, now you're starting to understand the loads that are put on buildings. And then we finish it off with a wind gust of 1,200 pascals. Okay. What people don't understand, ASTM E2357 is an excellent test. This is what you saw. It's designed for buildings that are 3 stories and less, and for 80% of the buildings that are in the United States. 20% of the buildings in the United States, even if they're 3 stories and less, it's not strong enough. If you're over 3 stories, you've got to go to your wind engineer. Depending on when you are, you may still be okay, but it could be completely different. And then, and the reason why we say 3 stories and less is why. Why is the height of a building important when you're talking air barriers? Yeah. So where do we measure our wind load? Like if you go on the TV and it says, you know, the wind is 20 miles an hour, where's that measured? Not quite ground. 30. So you're pretty close. So we measured at 30 feet. Why is that important? What happens if we do go to the ground? Because when we do a whole building test, we have tube plate on the ground. What happens there? What's the wind speed there? Yeah, almost nil. Let's go up the building. What if the building's more than 3 stories? Why should we care? 3-story building, let's say that's 40 feet high, just for rough figures. What if we go to a 10-story building or a 20-story building? Why is that important if we're talking about air barrier assemblies? Yeah, the same wind, same day, same location, completely different pressure difference. I think I have a slide on it. There's the 80%, 3 stories. Okay, so let's go to Boston. So the red is the 1 in 50 hourly wind pressure difference. And by the way, with climate change and everything, this is all being redone. And there's a person that's working for the Department of Energy and for the codes. They're trying to determine not history, which we build our codes on today. What do we need in 2100? And it's scary. But anyway, you do the 51 hour, 50 wind pressure, and depending on where you are in the United States, you'll pick one. I go to Boston because it happens to be the highest, 1,000 pascals. That's at 3 stories, like 20 meters. There's about 3 feet to a meter, 39 inches. So let's say 60 feet off the ground, you have a pressure difference at the top of the building of 2,410. Okay. Let's go to 120 meters, which is roughly a 400-foot high building, same location, same wind speed, recorded at 30 feet. What is the pressure difference? 5 times, 5.5 times. Why is that important? Take a normal window, subject it to 5,500 Pascal pressures. If it hasn't been designed to be in a high rise, it will blow apart. The frames will actually twist, the glasses will touch each other, and eventually it's glass all over the place. Why doesn't that happen? Well, we've got wind engineers that says we're going to put windows in high rise, they got to be different, they got to be stronger, and all the rest of the stuff. But again, goes back to air barriers, because you're going to have air barriers at a 400 high foot building. And so that's the loads. Again, our saving grace is most of the material is stuck to a substrate that's been designed for these loads. And typical degradation, this is a brick veneer swimming pool. That is a snow fence, and at least you guys know what a snow fence is. I got to explain that when I'm in Texas. Green grass and so on. And it's really hard to see, but the bricks are literally falling off. And there was another city, it was a 12-story apartment block, same type of thing. Bricks were flying off, and so they had to build a roof canopy over the sidewalk so the tenants could get into and out of their apartments. They really didn't appreciate getting hit with a brick. And you see this all over the place. This is actually up in this area, the picture down here. If you remember, a lot of it was in Vancouver, BC. It's called the BC condo crisis, a $3 billion repair job. That's a condo in BC in those days. And most of it was liquid water coming from the outside, and there's a whole bunch of reasons why that happened. But it was also water vapor coming from the inside. If you ever want to read it, it's about 600 pages long, and it's called the Barrett Commission Report, and it blames everybody. And it's not wrong. I had a bet with one of the guys that was doing investigations, and I said it was the installation. And what the report says is everybody's to blame. The province of BC, and specifically the city of Vancouver, decided they're going to charge you property taxes on your outermost dimension. What do you think happened to the eaves? They're gone, okay, because we could save 4 feet. And when you don't have eaves, what happens to the water? Runs right down on your wall. And then the inspections weren't being done. Stucco lath was being installed backwards and upside down, and the list goes on and on. Mold and mildew. Black is not too bad. You don't want any mold, but when you see brown, don't touch it. Don't even go near it. And again, another swimming pool, roof wall connection being a problem there. So we had to step back and said, okay, we started out with thermal fusible air barriers in Canada. They were basically torch-on roofing that we then torched on the walls. Actually works really good on CMU because the molten asphalt, you can get pushed right in there. Never took off in the States, open flame on a construction site. Nobody likes that. So didn't really see any down here. We went to self-adhered membranes because it's nice and easy to work with. And then we moved to more fluid applied, and now we have a whole slew of things. You're going to get a copy of this, so I'm not going to go through it in all details, but you can see we got building wraps, mechanically fastened or sandwiched and fluid applied, and they could be membranes and coatings. And the reason why we have the two of them, coatings is material that is so thin that it won't support itself, so we can't pick it up. Whereas a membrane, you do it on a release paper, and then you pull it off, and you can do all your testing. And the reason why we do that is then the substrate doesn't matter. All the testing is done on the air and water-resistant barrier material, so it can go on any substrate. Once you jump to coatings, you have a substrate. So now you have to test on gypsum board and OSB and plywood and CMU. And so you're 4 times the cost for testing. And then self-adhered, fully adhered. We've actually changed from fully adhered to self-adhered because in some cases it's not completely fully adhered. Pitch-a-thin base, been around forever. New material is polymeric based. That is designed to have a higher water vapor transmission rate. And so it's, I know if Kevin was here, he'd shoot me, but I call it house wrap with glue on one side. And it's a much more robust than that, but that's the idea behind it, to be more vapor permeable than asphalt self-adhered. And then you got masonry, stone composites, and you can have metal panels and composite panels and concrete panels and sheathing materials, insulating and non-insulating. Insulating would be polyiso and extruded and so on. Non-insulated, the OSB, plywood, et cetera, And then we have factory composite, and this is where you put the air barrier material on in the factory. There's at least 2, I think, or 3 manufacturers. So it's generally a gypsum company that buys an air barrier material and sprays it on the board before it goes out. And the idea behind it is that's all done in climate controlled, so you don't have wind and rain and so on. You still got to do all the joints. So when it comes to the job site, you still got to do all the joints and all the fasteners and everything. And it's also to reduce the amount of labor on the job site. But it's still, you got to do all those transition membranes to the doors and windows, penetrations, everything. And then we got all sorts of spray foam, low and light density. Low density, sometimes called 1 pound foam. Light density is half-pound foam. Medium density is 2 pound, and 3 pound is high density or roofing material. And the bottom 2 are closed cell. The second one with low density, it's a mixture of open and closed cell, and light density is open cell. So for it to qualify as an air barrier material, you're looking at probably 2 feet of it, but for most cases, not going to be practical. And then we get into the roofing membranes. We're just starting to work on that. We have one manufacturer wants us to evaluate their material as an air barrier in the roof. It's not a roofing material. And I already mentioned we got the assemblies. That's something we needed to be able to look at that. And we got all the different types, and we're going to work on them as we need to. And I'm not really saying that right, but if nobody's interested in having their material being an air barrier, we're going to work with manufacturers that do want us to help them be recognized as an air barrier. But eventually we'll work on. And then the next presentations, you're going to hear all about waterproofing materials, which by default is also an air barrier. And obviously they're a water resistant barrier. So material specifications. Okay, let's go through this. Now this is for fluid applied membranes. Okay, so this could be 1 component, 2 component, co-spray, could be a bunch of different things. Here's your standard. Now here's your table. This is a summary of all the requirements in there. So the first one is air leakage rate of the material. Makes sense? Okay, we talked about the air leakage rate or the permeability of material. And we also have, it's going to be the fourth one, we got fastener air leakage rate with modified specimen. We have actually just finished through the research committee, the research committee developing a standalone test for the air leakage rate of fasteners. And it's finished with the research committee. It's got to go to the board for final approval. And it saves a lot of wording within the material specification. And we have labs that are already being accredited to conduct those type. We get into alkaline resistance. When would alkaline resistance be of a concern to you? Saltwater environments could be, but there's going to be something that you're going to be dealing with no matter where you are. Yeah, there's alkaline in there, and if it's not, that's a compatibility issue. So we do a test, pretty simple test to go through there. Elongation is how much we can pull it apart. We have people that says, who cares? I think that's an important because that gets into spraying or install your material across a crack or a joint, and that material is going to move. So if you have a material that can't move and crack, or it'll crack, you kind of want to know that. I was approached by a manufacturer that does ceramics and goes, well, we have a perfect air barrier. True. And I says, now, when we put on buildings, buildings move. So are you changing your process? Are these going to become flexible ceramics or whatever? And they said, we'll get back to you. And that was like 5 years ago. So I think it's important that we could have freeze-thaw resistance. Obviously, if you're down south and it never gets below freezing, you don't care. But most manufacturers want to sell their material all over North America. So we have to be a little bit concerned about that. Fungi resistance really has nothing to do with air barriers. But we get the question all the time. Will this abort mold growth? So it's a cheap test, it's an easy test. We throw it in there because we want you to have all your information from a single source. Gap bridging ability, that sort of goes with elongation, but we literally have a gap in two pieces of specimen. We put your material across, and then they pull them back and forth. And does it have that elasticity, or will it crack type of thing out there? And that is it's an Abbott test method, T0004. Low temperature flexibility. This is basically a roofing test. And it's simply you wrap around the material around a mandrel of a certain size at a very low temperature. And does it crack? Kind of important if you're putting self-adhered membranes on walls at very low temperatures. Peel adhesion. Peel adhesion and pull adhesion is going to tell you how well your material sticks to the wall. And they're two different tests. They give you two different numbers and for two different reasons. So we have both of them there. In peel adhesion, we take basically a 1-inch strip and we pull a little bit off, and then you pull it down at 180 degrees. And what is the force that you need to be able to have it start to peel down? Pull adhesion is the same thing. It's a 2¼ inch diameter disc that you glue to the wall, you cut around it, and then you pull it off. There's two manufacturers of portable pull adhesion testers, and you get a number. The average number, by the way, for all materials and all substrates in every place in the United States is 23 PSI. We did a whole research on 5,000 different reports of pull adhesion being done in the field. And we expected different materials would have different rates. And we expected the same material on different substrates would have different rates. We were really surprised that that difference was very little. The range from the worst, and we got some outliers, but the range was basically between 20 and 23 PSI. Doesn't matter the material, doesn't matter the substrate. And that surprised us. And we really expected gypsum to come in around 4 or 5 PSI before it come apart. And it didn't. It was around, if we do the average, about 21 PSI. Now we do have an issue in the field where when we do the pull test, the facer of the gypsum comes off. And so our research committee is working on how do we determine whether the substrate's acceptable if it's gypsum board with some sort of glass paper face. Surface burning characteristics, the code wants that. So that's that E84, the tunnel test. How far down the tunnel does it go? And VOCs, very important in some cases. Other states couldn't care less. So we put that in there just so you have it. And then you get into the water one. So water absorption by diffusion. Why do we have that test? Actually, the title of this should be changed to isotopes. And I forget the whole list on there, but it's basically water vapor going into a solid material. It's really what it comes down to. Why is that important? We're talking about the air barrier material, not the framing, not the gypsum board, not anything else. Why do we want to know if we put an air barrier material in a high humid condition, whether all that water is going to go into the air barrier material? Yeah? What could happen to the material? And we have some cases where the material emulsifies if it's a fluid applied and runs down the wall. If it's on the floor, it doesn't work as an air barrier in the wall. I'll guarantee you that. I don't even have to say it depends. So we want to know that. And then you have water resistance, 100% relative humidity. It's very similar to that. And then we have the water vapor transmission rate, both water and desiccant. I'm going to dwell a little bit on that. So that's a typical material specification. Every material will have slightly different things depending on what you want. But we also have the pass-fail. And if you take a look at water vapor transmission, we just say report. So why would we say report? Because that's so important, right? Water vapor transmission rate of materials. We want to know if it's a class 1, class 2, class 3. So why don't we say all of them have to be at least class 3? Yeah. We used to have permeable versus impermeable when we first started out, when every state had one perm as the, got to have a vapor barrier and it's got to be one perm. So then we said anything above one perm is permeable and anything one perm and less is impermeable. Now, when they changed it to 3 classifications, and then if you go to the next one, which they don't talk about, which is above 10 perms, that's 4 different. So we would have 4 different material specs on there. And then we said, that's stupid. So we asked for the report. Those numbers show up on our website for all the materials so that you will know exactly the numbers for the water vapor transmission in both desiccant and water. So we've punted it to you guys to determine what you need on your building, whether you want it highly permeable, very airtight, water vapor tight, and so on. And we've done that a few cases. Again, VOCs, states set the limits for there, so we just say report. So you saw this. Remember I said we do the testing 25, 50, 75, 100, 150, and 300, and then we report at 75. So that's the easy one. Density is pretty straightforward. We take a piece of material, we measure all 3 dimensions for it, and we divide the weight into it. So we get, whatever the density is. Length, width, and height divides into the weight, gives us the density. Most people don't care about the density unless you're into spray foam. Next one we talk about is compressive strength, and that's an important one for a lot of materials. Spray foam is a good example. After dimensional stability, then the most important one is your compressive. If you have the right compressive, which is generally around, for medium dense, about 40 psi, then you know all your other material properties are the same, are going to be good. Your water vapor transmission rate, your heat flow, everything else, because you know you got the right material there. And you're looking at the value that you get at 10% deformation or at break. Because as you see, you're going to see it goes up and you got 3 different ways. But at some point, you're going to get that top, at the top of it, and that's going to be the value, even though it could be at 10% or it could be at deformation. Atmospheres, we talked about for spray foam, dimensional stability is really, really critical. So we test that at -20 and 80 and 70 degrees and 97% relative humidity. It goes into the oven, that's all controlled. We do it for 28 days. Out of all those 3 atmospheres, what do you think is has the most effect on a material? Probably the cold, right? Because everything's going to shrink and so on. Actually, hot and humid will have the biggest impact on how much material, what happens to the material. And most materials will expand and then shrink. So that's why the 28 days is important. Some people do it for 7 days, but has it done, whether it shrinks and expands or expands and shrinks, has it went through that whole thing? That's why we require 28. And most material standards are out there. Mold growth, like you do a comparison, you put your material on one, you have another one that has nothing on it, and you're looking for no mold growth, you use certain bacteria and all the rest of the stuff. Pretty simple test and straightforward. Here's a very simple explanation of the gap bridging. 2 pieces of substrate, put your material on it, move it back and forth about 3 millimeters. I think it's like 50 cycles. And you can do it at different temperatures. Some of the temperatures is -20. Other ones are more 40, 50 degrees. Closed cell, I was hard to sort of show that. Basically, we pump air into it. And so we know by how much air we can pump into like closed cell polyurethane, we know how much is open cells and how much is closed cells. Doesn't really tell you anything, but we typically classify materials as open cell or closed cell. And I don't know why, but we've always done it. Here's your pull test. This is the Abbott T0002. Compton and force test, 2 different ones, basic principle. We attach the 2 1/4 inch disc to the wall. We separate the material around the 2 1/4 inch disc, so we're only pulling on that. And then we rotate that handle in a nice smooth fashion, and we determine when there is a release. If you take it and you crank it like you wouldn't believe, you're going to get a really high number. But we learned a long time ago that a low pressure over a long period of time will peel air barriers off a wall, whereas if you're trying to really grant them, they will stick like crazy. Tunnel test, showed you that picture before. Tensile strength, we're pulling things apart. So when is it going to crack if there's movement in the building? Heat flow, this is called a guarded heat flow meter, or guarded plate. It's basically, we've got a cold plate and a hot plate. We put the insulation in between there, whatever we're measuring, and we can measure the amount of energy that we need to keep the delta T across it. Normally it's a delta T of 22 degrees C. And it's tested, all insulation is tested at about 23 degrees C. Why we need to test it at 23 degrees C, or why do we need insulation at 23 degrees C? We don't really, but that's, again, standardized test methods. Water absorption, when we're putting it in, we sink it, we measure it, the weight before, weight after. We know how much water's went in there. Here's AATCC. This is called the water resistive test. You've got to be careful in this one. It's really good for thin materials. If you have a self-adhered or a fluid applied and it's 1/8 of an inch thick, you can put it in here, and you have 22 inches of water and you let it sit there for 5 hours. And then you look on the other side and you're looking for drops of water. I think it's very subjective. When should you never use this test? No wrong answers. Come on, guys. Exactly. I can pass this test with gypsum. Now, the gypsum is full of water. It's mush, but I don't get drops on the other side, so I pass. Got to be careful with some of these. That's the whole point I'm trying to make with some of these. Here's your water vapor transmission. You got automatic machines, or the old way, you had your desiccant and water where it says 4. In a glass disc, typically you put your air-bearing material or whatever material above it, and then you put it in an oven. The oven is 50% relative humidity, again 23 degrees, and with a desiccant in there, technically it's 0 inside. Water is 100%, so you're either going from 0 to 50 or from 100% to 50. So it's water going in and water going out. We can measure the weight of that. That's a cell, so we can measure it instantly at any times. And so some of the materials to do the water vapor transmission rate has to be in that for like 6 or 8 months. So we get enough water, we can actually measure it. This is one that you really have to be careful, because if you sort of look at it in a very simple way, we're talking about how water goes through material at 23 degrees C and at either 25 or 75% relative humidity. How many times, and the code says you got to do the desiccant, so that's at 25% relative humidity. Think of your wall cavity, think of your atmospheres you have here, your weather. How many seconds in a year is it going to be that exact atmosphere? And I did say seconds, okay? It's, if anything, use the water method because that's more accurate, but it's going to change hour by hour, minute by minute. It's going to be all over the place. And again, go back to what it says in the material specification, not to be used for or to determine end use performance. So this is where we get all the confusion. Here's the reason why. I went to our website. As I say, all the water vapor transmission rates are on the website. I took the same material. We got one material that has, now these are nanograms. This is not perms. There's 57.4 nanograms to a perm. 5 nanograms to 5 nanograms. I'm going to round them off. That's the same material. So it doesn't matter if it's desiccant water, that's going to do the same. Take a look at the mean, and what I mean by mean, because if I look up in the dictionary, it's all over the place. If you have 100 results, it's what's the middle one. And that gets you from averaging. Averaging, you could have a whole bunch of really bad ones and then normal ones, and so you skew it. But we got the mean and then the maximum. Look at the maximum. What's the percentage difference? And that is not a typo. So you're going to use the desiccant method, the water vapor transmission rate in your project because you think that it's 4.3 nanograms, not perms, nanograms. But in most of the cases, you're going to be sitting at least in the water. So we're up to 1,800 nanograms, 42,000% difference. Same material, just different atmospheres. And I went through all of them. So Again, the minimum, some of them are pretty darn close. The maximum goes from 943 to 2026. Every time you change the atmosphere, you change the number. And this is a curve you're going to get, and so on. This is your isometric chart that everybody's familiar with and works, and so on and so forth. That's really why we want to deal with that. So if you want to do all this work yourself, you can do it. So you want to determine, if you pick up a material, let's say, you know, this is not quite peanut butter, but let's say I decided I wanted this to be an air barrier and I wanted to sell it to you. I can give you this piece of paper. So then you got to come back and say, well, what are the key properties for this material? Do you want elongation? Do you want dimensional stability? Do you want compression? What do you want? And then what's a test method that you want to use? You have to decide this. For every one of those key properties, how do you want me to test? And then once you get the testing done, is there a minimum or maximum? What's the baseline that you want and for your material that you're going to use in your project? And then if you get the test method and you got the minimum maximum, how do you decipher the test report? And then how do you compare one material to another if your testing is different than somebody else's testing? That's why we do standardized tests, so we can compare materials. You can all do that, or if you open door number 2, you go on the ABBA website and we got it all done for you. Okay. We're just really nice guys. There's the different materials, and you can go in if you want to see all the different test methods. You go in and get evaluated, and it'll ask you, and it'll point you to the material specification. This, I'm almost out of time, but this is important. This is the energy saving, the moisture transport calculator. And it's really to reinforce the point that water vapor going into the buildings is huge. So this is in metric, 7.5 is the average one for buildings. I took it down to half. These are all archetypes that are out we use for codes. The two key things here is you have the base case. In this particular, it's not letting me do that. Okay. So the base case you see under ELA, 26 square feet. That's all the holes added together. And how many gallons of water? I think the next slide makes it bigger. No, it doesn't. 135,000 gallons are going through that 26-foot hole. I think that's a lot of water. And that's water vapor. How about this one? Now we got a hole that's almost 140 square feet. How many gallons? If you're sitting in the back, it's 592,201.55 gallons. Do you think you got a problem? And yet we don't think about it that way, you know? So we have the quality assurance. We found that no one thing can help you guys. We have to have proper standards. We have to have proper specs. We have to have evaluation. We have accreditation of contractors, training and certification of installers, site audits, and so on. That we can help you get a building built right. That's it. Any questions? I have this guy looking over my shoulder, giving me the dirty look, but I can take one. No questions. You guys should be feisty. You should be saying, that is wrong, I disagree. And then we can have some real conversations. Thank you so much.
Thanks again, Laverne. Now it's time for another 15-minute break. So please help yourself to the refreshments, the restrooms in the lobby, and we'll be back at 2 for the final session. Thanks.